Let's do another problem involving a discrete probability distribution. So this is a Chapter 7 problem right out of Siegel, or you can find it in your course packet. It's around page 113. So the length of time that a system is down, that is broken, is described approximately by the probability distribution as follows. So minor problems. So think of this as you've got a random experiment. The random experiment is the computer system goes down. Now what you don't know is how long it's going to take to fix. So minor problems take 5 minutes to fix. So you can think about some event of minor problems. So if it's just a minor problem, it's going to take 5 minutes to fix. We're assigning a number to that outcome from the random experiment. These occur 60% of the time. Substantial problems, another event, require 30 minutes to fix and occur 30% of the time. Catastrophic problems require 120 minutes to fix and only occur about 10% of the time. These are the only 3 types of problems, and assume that they always take this long, 5, 30, or 120 minutes. Now, you want to recognize that this is a discrete random variable because you have a countable set of outcomes, or events, minor, substantial, and catastrophic. Each one of these have probabilities, and there's numbers that go along with each of them. So this definitely puts us in the class of a discrete probability distribution. That happens to be the answer to part A. Let's read ahead. We need to find the mean, the standard deviation, and then some probabilities about this thing. Well, whenever you need to find the means and standard deviations of a discrete random variable, use Ed's table. So let's go over to Excel, and we're going to make Ed's table. Now the first thing that you probably want to do is identify your random variable. So let's say that X is the random variable indicating the downtime of a computer. All right, so we've had this random experiment. The computer goes down. X is the amount of time it takes to fix it. Now, if you think about Ed's table, you always have X, then the probability of X, and then X times the probability of X. So let's go fill in these rows. So one event could be the problem is minor. In that case, it takes 5 minutes to fix, and let's see, those things occur 60% of the time. Another possible event is that it is a substantial problem. Those things take 30 minutes to fix, and they occur 30% of the time. The third possible outcome is that it is catastrophic, in which case it's going to take 2 hours or 120 minutes to fix. These occur with probability 0.1. The other thing that you want to do is put the sum in this bottom row. So let's start by finding the sum of B, in my case, B4 through B6. I could also highlight those if I want. And what you'll see is that they add up to 1. If they don't add up to 1, you've done something wrong. So it's just a good way to check your work. Always see if they add up to 1. Now let's go fill in this next row with Ed's simple table. So that is always just X times the probability. We're going to give weight 0.6 to 5 minutes, and we're going to give less weight to the other ones. Now I can copy this down, and then I can also copy the sum. So if you notice what I have in this cell, I've got the sum of C1 through C6 now. The mean is 24. So let's just write the mean here. The mean is that thing. Now let's get the variance. Now if you remember, here's what we have to do to find the variance. This gets a little bit tricky. We're going to take the squared deviation. So what is the squared deviation? Well, that's going to be A4 minus the mean. Now I want to hold the reference to the mean constant. I could just type 24 in, but I think it's better practice to reference that cell. So this is, the mean's going to be in C$7. So again, the $sign holds that cell reference constant when I copy this thing up or down. Close my parentheses, and I square it. So that's the squared deviation from the mean. Now I have to assign an appropriate weight to this. So if I multiply this whole thing by the probability, which is in B4. I get the weighted squared deviation. And okay, having done that, I can copy it down. Let's copy the sum over. This gives me the variance. So the variance is 1149. Now the thing is, the problem wants the standard deviation. So the standard deviation is just the square root of 1149. So I take the square root of that number. The answer to this problem, the answer to part C, is going to be 33.9 if we round correctly. So let's go back to the course packet. So the mean downtime is 24. Let's check my work. Cool, I got the right answer. The standard deviation was 33.9. Okay, cool. Looks like we got the right answer to that one as well. Let's look at part D now. Part D says, what is the probability that the downtime will be greater than 10 minutes? All right, well, let's go look at our table. Which of these events constitute a downtime greater than 10 minutes? Well, certainly these two do. The first one doesn't, it only takes 5 minutes. So the probability, the way we would write this is, what's the probability that x exceeds 10 minutes? And this is just going to equal the sum of these two. So 0.3 plus 0.1, and the answer is 0.4. So there's a 40% chance of a downtime being greater than 10 minutes. And sure enough, that is the correct answer. Let's go on to part E. Part E reads, what is the probability that the downtime is literally within one standard deviation of its mean? What would you expect from a normal distribution? Okay, well, do we have a normal distribution here? The answer is no. I'm going to go over to the sketch pad for a second, and let's just draw out this distribution. So this is x. Here is the probability of x. And somewhere around here is a 5-minute downtime. Then you get a 30-minute downtime. So 30, here would be 60, 90, and 120. Now, if we write in some probabilities, let's make this 0.6. This would be 0.3. So here is a bar for 0.6. The 30-minute ones occur 30% of the time, so you get a bar here. And the 120-minute ones occur 10% of the time. So this surely isn't normal. Now the mean is out here someplace at 24. So the problem asks, what's the chance that we're within was it one standard deviation of the mean? Let's go read this again. One standard deviation of the mean. So what do we mean by that? Well, 34 plus the mean. 34 plus, so 30, I'm going to round the standard deviation to 34, and the mean is 24. So if you go the mean plus one standard deviation, which I'm rounding to 0.34, is going to be 58. If we take the mean minus one standard deviation, you're going to get about minus 10. All right, so if you go within one standard deviation of the mean, you capture all of these values. Right, so it's everything but this bar. That bar does not count. So the probability, if you want to write this in very formal ways, so what's the chance that we are between minus 10 and 58 is going to be everything but that last bar, which is 0.9. Now this is quite different than what you'd get with a normal curve. Recall that if you have a normal curve, the chance that you're within one standard deviation of the mean, if this is the mean, you go one standard deviation out, so this is sigma, and this is sigma, that chance is 68%. So the reason this doesn't equal 68%, 0.9 does not equal 68%, because this is very right skewed. So we wouldn't expect it to equal 68% since it's not normal. Okay, that's this problem. Go try it on your own.